Hello guys, welcome back to my YouTube channel. I am Chandan Kumar KV studying in Sri Venkateshwara College of Engineering, wearing the USN 1VE 21EC018. Today I am going to introduce you all to the VLSI fabrication process and the journey from a silicon to a chip. So VLSI fabrication is known as the very large scale integration process which mainly produces the microchips. This process transfers the pure silicon into complex miniaturized devices that power the modern world from smartphones to a supercomputer. Let us see the wafer preparation and cleaning. Crystal growth. The journey begins with a perfect crystal of silicon carefully grown into a cylindrical ingots. These ingots are then sliced into thin circular wafers typically around 300 mm in diameter. These wafers undergo polishing to achieve a perfectly flat and smooth surface, free of any imperfections. A series of etching process then removes any remaining impurities and prepare the surface to fabrication step ahead. Cleaning and inspection. The wafers are subjected to rigorous cleaning procedures using the specialized chemicals to remove any contaminants. After each cleaning steps, they are inspected to ensure they meet the highest standards of purity and cleanliness. Film deposition techniques. Sputtering. Sputtering involves bombarding a target material with ions, causing the atoms to be ejected and deposited on the wafer's surface, forming a thin uniform layer. This method is widely used for depositing the metal oxides and nitrides. Chemical vapor deposition. The CVD reactive gases are introduced into a chamber containing the wafer. They are reacted and deposited on a thin film onto the surface. This process is used to create a variety of materials including the silicon dioxide, silicon nitride and polysilicon. Atomic layer deposition. ALD is a highly precise deposition technique that involves alternating the chemical reactions on the wafer surface, resulting in the atomic level control over the thickness and uniformly of the deposited film. Evaporation. Evaporation techniques involves heating a source material in a vacuum chamber, causing the atoms to vaporize and deposit on the wafer surface. This method is often used to deposit the metals such as the aluminum and gold. Polylithography process. Photoresist application. A photosensitive material called the polyresist is carefully applied to the wafer surface, forming a thin uniform layer. Photoresist acts as a mask, protecting the certain areas of the wafers during the subsequent etching process. Exposure. The wafer is then exposed to the UV light through a patterned mask. The mask allows the UV light to pass through the specific areas, exposing the photoresist and causing a chemical change within the exposed regions. Development. After exposure, the wafer is immersed in a developer solution. The exposed regions of the photoresist dissolves, leaving behind a pattern that corresponds to the mask design. The unexposed regions will remain protected. Etching and the pattern transfer. Wet etching. Wet etching involves immersing the wafer in a chemical solution that selectively removes the exposed areas of the wafer. This process is relatively simple and inexpensive, but can be less precious than the dry etching. Dry etching. Dry etching utilizes a plasma of reactive gases to remove the exposed areas of the wafer. This method offers the great precision and allows more complex patterns to be etched. Pattern transfer. After etching, the photoresist is removed, revealing the desired pattern on the wafer surface. This pattern is now ready for the subsequent fabrication step, where it will be used to create the interactive features of the integrated circuits. Ion implementation and doping. This process involves bombarding the wafer with ions of specific elements such as boron, phosphorus, or arsenic. This ion penetrate the silicon lattice, changing its electrical conductivity and creating the desired doping profiles. Doping. Doping is the process of intentionally adding the impurities to the silicon crystal lattice. The controlled addition of the impurities allows to create the p-type and the n-type regions where, where the silicon, which is essential for forming the transistor and other electronic components. Oxidation and dielectric formation. Thermal oxidation. Thermal oxidation is a key process in the VLSI fabrication, where the wafer is exposed to high temperature, causing a thin layer of silicon dioxide to form on the surface. The silicon dioxide acts as an insulator, preventing the electrical current from flowing between the different layers of the circuits. Electrical formation. The formation of the dielectric layer is crucial for isolating the different components and preventing unwanted electrical connections. Dielectric materials such as silicon dioxide have low conductivity and high resistance, making them ideal for this purpose. Dielectric properties. Dielectric plays a critical role in the VLSI fabrication by providing the insulation between different layers of the circuit, controlling capacitance, and preventing the leakage of currents. Metallization and interconnect layers. Metal decomposition. A thin layer of metal, typically aluminum or copper, is deposited on the wafer surface. This layer serves as an electrical connection between different components of the chip. Via formation. Via vias which are small holes etched through the dielectric layers are used to connect different metallization layers, allowing the electrical signals to flow between different levels of the chip. Testing and quality control. Probe testing. During the probe testing, fine needles are used to contact the pads of the fabricated ICs. Electrical signals are applied to these pads and chips are functionally is evaluated under various operation conditions. AOI. AOI involves scanning the wafer surface with specialized optical microscopes to detect any defects or imperfections in the fabricated circuits. Parametric testing. Parametric testing measures the electrical characteristics of the fabricated circuits such as resistance, capacitance, and voltage. This testing verifies the device meets the design specifications and performs as expected. Packaging and assembly. Die separation. The wafer is diced into individual chips, each containing a complete integrated circuit. The chips are then inspected and tested once more to ensure that they are functioning properly. Assembly. The packaged chips are then mounted onto a printed circuit boards along the other components to create the functionally electrical devices. This assembly process involves careful soldering of the chip's pins to the PCB, ensuring the connections are secure and reliable. Thank you for your precious time. Please do like, share and subscribe.